Physicists, generally speaking, spilled over with assumption as they saw the long-expected initiation of the most powerful high-energy particle collider after industriously keeping it together for the overwhelming majority of the years since they last saw this vital advancement, which was adjusted to change our understanding of the universe. The Immense Hadron Collider, operated by the European Organization for Nuclear Research, became operational in September 2008 after a painstakingly prolonged improvement stage. At any rate, it took the machine planners a seriously drawn-out period of time to perfect it. Since then, the tremendous Hadron Collider has played a vital role in unraveling different conundrums of the universe during its unique exploratory runs. However, continuous upgrades have raised stress among scientists at CERN. After ramping up the Large Hadron Collider to another energy level, they perceived something endlessly frightening. Assessments have incited unique theories attempting to get a handle on this quirk, however, they remain unsubstantiated and theoretical. The universe has an enormous number of unexplained mysteries, and over the years, scientists have dedicated their time to exploring and attempting to grasp some of them. These mysteries include the gigantic black holes seen in space, which are said to have a gravitational pull that even light can't escape. Moreover, there's the riddle of what lies under the Bermuda Triangle, often called Satan's Triangle, renowned for the mysterious disappearance of more than 50 ships and 20 planes. However, these secrets remain unexplained due to the limitations in technology during the 20th century. Physicists sought better ways to research the fundamental building blocks of matter. In 1932, physicist John Douglas Cockcroft and engineer Ernest Walton assembled the first practical particle accelerator. These particle accelerators are major devices for exploring the fundamental constituents of matter by accelerating particles to high energies. By colliding them, scientists can study the ensuing interactions and test the fundamental forces and particles that make up the universe. Considering how significant particle accelerators can be in making sense of the secrets of the universe, CERN has built the world's largest particle accelerator. Nonetheless, scientists have raised concerns that this atom smasher could potentially cause the Mandela effect due to its ability to alter the fabric of space and time. What are the implications of this revelation? Many people can't resist the urge to contemplate why they remember things differently from how they actually happened. This phenomenon is known as the Mandela effect. The term was created in 2009 by Fiona Broom, who discovered that she and various others wrongly thought Nelson Mandela had died in the 1980s, while he actually passed away in 2013. Several factors can cause this effect, including false memories and the strong influence of social media and the internet. However, some researchers have raised concerns that past enhancements of the LHC might have also caused the Mandela effect. Before dismissing this revelation as a paranoid fear, note that several prominent scientists and notable figures have expressed concerns. Stephen Hawking was one of the first to voice his fears about the potential consequences of the Large Hadron Collider, warning in an interview that the collider could create black holes that might threaten the universe. Another researcher, Dr. Carlo Rubbia, shared his concerns in a blog post, suggesting that it might produce strange particles that could alter surrounding matter in unforeseen ways. Even figures in the realm of past science have spoken about the possible dangers associated with the colossal Hadron Collider. Astrophysicist Carl Sagan and science fiction author Arthur C. Clarke also voiced worries about the collider, suggesting it could create strangelets or even a black hole that could consume the Earth. In a discussion, President Obama also expressed his concerns about the collider causing a catastrophic event that could impact reality. The fact that a trivial few groups of notable people, from scientists to researchers and celebrities, have expressed unease about the LHC highlights the reality of the concern. While we can't predict the outcomes, it's crucial to carefully consider the potential risks and make informed decisions about operating the collider. Is the LHC capable of causing the Mandela effect and other changes in our universe? The Large Hadron Collider is currently the most powerful and generally reliable atom smasher in the world. It was built between 1998 and 2008 in collaboration with over 10,000 scientists from more than 100 countries. It became operational on September 10, 2008, and is the most recent addition to CERN's accelerator complex. The goal of this particle smasher is for physicists to test the predictions of various theories of particle physics, including assessing the properties of the Higgs boson, searching for the multitude of new particles expected by supersymmetric theories, and investigating other unresolved questions in particle physics. The collider is approximately 27 kilometers in circumference and is equipped with numerous structures that accelerate particles to higher speeds and energies. Inside the accelerator, two beams of energy particles move at incredible speeds, almost as fast as light, before they are guided to collide. These beams travel in opposite directions through isolated tubes called beam pipes, which are maintained at very low pressure. The beam pipes then follow a circular path around the accelerator due to the strong magnetic fields generated by the superconducting magnets. Lead particles are the preferred choice for this program, and they are accelerated to an energy of 2.3 TeV per nucleon, or 522 TeV inside the LHC ring. The LHC operates with an immense amount of energy and generates vast data sets, underscoring the scale and significance of this ongoing effort. The CERN site draws around 200,000 visitors annually. Mega of electrical power from the French lattice during LHC undertakings by and large honor of the energy usage of the city of Geneva strikingly. The LHC gas pedal and locators contribute around 120 megawatts to this solicitation. This energy beats the energy achieved by the relativistic Deep Molecule Collider. The Deep Molecule program hopes to examine quark-gluon plasma, a state of matter acknowledged to have existed, giving remarkable pieces of information into the nature of matter and the universe. With the help of this particle accelerator, one of the critical theories in particle physics concerning the existence of the Higgs boson particle has been shown. The Higgs boson, often referred to as the God particle, was discovered at CERN in 2012, signifying a significant forward jump in the field of particle physics. If you're wondering how the Higgs boson obtained its moniker, it's from a book named The God Particle, created by Leon Lederman in 1993. However, this nickname has drawn responses from various physicists due to its potential to mislead the public about what the particle represents. The Higgs boson is a subatomic particle in the standard model of physics created by the activation of the Higgs field. In the standard model, the Higgs particle is a massive scalar particle that has zero spin, no electric charge, and negative parity. It associates with mass. The particle is extremely unstable, decaying into various particles rapidly upon its creation. The Higgs field, shaped like a Mexican hat, is an invisible force field with different components that are both electrically charged and not. This field influences the way particles interact, giving them mass through something many refer to as the Higgs mechanism. The Higgs particle and its field are named after Peter Higgs, who, along with 5 other researchers, proposed the existence of the particle in 1964. This physicist, alongside his colleagues, proposed that the particle is the fundamental reason why certain particles acquire mass at lower energies. After searching vigorously for many years, scientists eventually discovered a particle with similar characteristics to the proposed Higgs boson in the LHC. Finding the Higgs boson was crucial because it helps us understand why certain particles have mass, a fundamental property that affects how matter behaves and interacts. To create Higgs bosons, scientists use 2 light beams and cause them to collide with each other at incredibly high speeds. Occasionally, a Higgs boson is produced as part of this collision, but it does not last long because it decays quickly. Since the Higgs boson disappears rapidly, scientists cannot observe it directly. Instead, they analyze the particles produced when it decays. From that data, they infer the decay patterns. If what they observe matches the predictions for a Higgs boson, it suggests that a Higgs boson may have been created. However, producing a Higgs boson in a collision is rare, and different collisions can appear to be similar. Therefore, scientists must examine data from trillions of collisions to be sure. They look for consistent patterns across different detectors to ensure that the findings are not just random events. Extensive coherent research has been conducted to investigate potential relationships between the Higgs field and the Big Bang, a speculative field proposed to explain the rapid expansion of space during the universe's early moments, known as the inflationary era. Several theories suggest that a significant atomic field, such as the Higgs field, could be responsible for this phenomenon. The destiny and nature of our universe have become subjects of examination because, according to the Standard Model, there is a possibility that the state of the universe, known as the vacuum, could remain stable for a long time. However, it isn't particularly stable, which means that perhaps the universe could become more stable in the future. This would alter everything we believe and understand about the universe. The properties of the Higgs boson are also critical in determining the stability of the vacuum that houses the universe. If the universe is in an unstable vacuum, it could lead to significant changes in the distant future. There is a need to precisely measure the mass of the top quark using a special type of collider known as the electron-positron collider to determine what might ultimately happen to the universe if the vacuum's stability changes in the future. Researchers also believe that the Higgs field is the energy that fills the vacuum, influencing the extreme energies of the universe's early moments. This idea suggests that the Higgs field underwent various structural changes over time while simultaneously creating the forces we observe in the universe. Scientists are currently investigating the Higgs field's relationship with the energy in the vacuum of the universe. The energy that is currently considered to exist in space is extremely low. However, theories involving the Higgs field and other considerations suggest it should be significantly higher. This discrepancy creates a major problem in physics known as the cosmological constant problem. Looking back at history, we can see how particle physics has enhanced our understanding of the fundamental building blocks of matter and forces. During the 1960s, scientists faced a challenging time attempting to unify the electromagnetic and weak nuclear forces using quantum field models. The theories they had, like Yang-Mills theory, suggested that certain particles, which we knew had mass, should actually be massless. This created a significant problem. There was also a theory called Goldstone's theorem, which proposed the existence of massless particles known as Goldstone bosons, adding to the challenges. Initially, scientists did not focus on this theory, but it eventually became very significant after Martinus Veltman and Gerard T. Hooft made substantial progress.